So basically in this study, so topology is a branch of mathematics and quite an important branch of mathematics which has applications in further subjects like geometry and so on. So at least in this talk, so to give an overview of this talk, so I would start by giving some examples of topological spaces which we start to look at and give a formal definition. And then actually if we want to look at good topological spaces which have a wider scope, so those are called as manifolds, so which I would introduce. And later actually we would want to look at some invariants of these topological spaces. So the invariants are usually introduced to distinguish your topological spaces, namely that you have suppose two topological spaces, so how can you say that they are not the same? So that means you attach certain invariants. So in this case they happen to be groups, and so the groups would be the fundamental group. So this is somewhat which measures the holes or rather one-dimensional closed subspaces of topological space. So if we want to look at higher dimensional closed subspaces of your topological spaces, so one needs to introduce a cohomology theory, which is the singular cohomology theory, which sort of measures or rather gives a fair understanding of higher dimensional closed subspaces of your ambient topological space. And so basic question here is to how do you realize these classes in these groups corresponding to some geometric object. So these are precisely coming from vector bundles, so which are another class of topological spaces, but which is actually sort of a covering space of your original topological space. And so we would end with a relation which which attaches the invariants of these vector bundles to the invariants of your topological space. So this is the Chern character isomorphism. So this is basically to give an idea about why invariants are useful in the study of topological spaces, and why the study of vector bundles is also relevant to understand the classes which can be attached to topological spaces. So since this is the last talk, I suppose many of you would be tired, so I hope this is quite a light talk. So if you have any questions, so please feel free to ask. So as I said earlier that topology is a study of spaces. So the simplest topological spaces which we encounter in our undergraduate classes are the Euclidean spaces, the real line, the real plane, and the n-dimensional real space. So these are the normal usual Euclidean spaces for any n. So n is, we know intuitively, so this is the dimension of your Euclidean spaces, and the main feature of these Euclidean spaces is the existence of a metric, so which we know is just a distance function on your n-dimensional real space. So what is the point in having this distance function? So it is basically saying that it enables us to do calculus. So calculus essentially means that you can differentiate and integrate functions on your Euclidean n spaces. And another feature, which you can, so to do all this differentiation and integration, so usually we start with some epsilon delta theory and so on. So that basically says that in terms of topology, it's saying that you can define some open subsets in your Euclidean n spaces, and which allows us to define continuity, differentiation, and so on. So topology is relevant to define all these objects. So actually if we want to make this study in an abstract way, so what do we do? So basically the relevant things which enables us to do all to define continuity and so on is the notion of open sets. So you just start with any set and non-empty set, and then you define topology is actually just a collection of sets, or rather subsets of your ambient big set, and these sets you call them as open sets, and they have to satisfy certain axioms, namely the whole space and the empty set, so they should be called as open subsets. And then we also require that arbitrary union of open sets and finite intersection of open sets is again open. That means the arbitrary union of sets in this collection of subsets, so this should again be an object in that collection. And then if you take finite intersection coming from this set, it should again qualify to be in this collection. So with this collection of sets, subsets of your ambient space, so this we say forms a topology on your set. And now you see that it would make sense to define continuity of function and so on, and but it doesn't really give us information how to differentiate or integrate functions. So at least we begin with some normal properties. So any metric function, I mean if you take any metric space, it defines a topology where you can take your open sets to be union of your open balls there, any arbitrary union of open balls. So you take the collection of all such things, so that defines a topology on your metric space. And then the normal properties like Hausdorff, compactness, boundedness, you can extend. So these properties already exist on metric spaces, which you are familiar with. So you can extend these properties to topological spaces as well. So I don't want to go into the definition. At least in this talk, I just want to give a more intuitive idea of the concepts involved rather than go into rigorous definitions. So actually, I mean if you open any book on topological spaces, I think there would be several other properties like T0 property, T1 property, T2 property and so on. And T2 property, which you may know, is just the Hausdorff property, saying that given two distinct points, you can separate them by finding disjoint neighborhoods which contain them. So this is T2 property, and so you have several variants and different kinds of topological spaces according to the properties which they possess. But actually what, at least we want to study topological spaces by not looking at pathological examples, but rather in a broader context. So the broader context would be which has applications in other subjects, so mainly in geometry. So geometry, we know, so this is actually a study of good topological spaces. So I would say what we mean by good topological spaces. For example, you can keep in mind the usual Euclidean n space. So this is a good topological space, and so with additional parameters to enable calculus. So this motivates a definition to define good topological spaces. So these good topological spaces, we would call them as, or rather they are called as smooth manifolds of dimension n. So these are some spaces which are which look like your Euclidean n space, at least locally. So locally what you have in your n-dimensional Euclidean space are the open disks. I mean you have, you start with your n space. For example, this is your two-dimensional plane, and then you choose any point on your plane, and then you have different neighborhoods of radii r and so on. So this you can do for any given point. So you look at this collection of all these open subsets of this open disks. So you get a topological space, but we say that it's a manifold of dimension n. So basically, when you define a topological space, and suppose if you have this property that it is covered by open disks which look like Rn, at least you have the notion of dimension attached to a topological space. So this is why we mean when we say good topological space, we need certain invariants attached. So the basic invariant is the dimension of your topological space. So this we can do only if we know that your manifold or your topological space locally looks like. So suppose I have a topological space in this manner, call it M. So I look at any point, so this is the filled one. So if I take any point on M, so I can always find some open subsets. say whatever is the radius, and this open ball. So this can be realized as an open disk in R2. So you see that this I can do it for any point on this topological space, which is this filled figure. And now once I have this identification, one can immediately say that because any open subset is identified as some open ball in R2, I can attach the notion of dimension to this topological space. So in this case it is 2, right? So when we require such a condition, at least we get an invariant which helps us to distinguish topological spaces. For example, if I take a topological space which looks like something like this. Okay, maybe I don't want this kind. Okay, something like this. So here also you will see that if you take any point P here, so any open neighborhood, one can choose it, or rather if it has some open neighborhood which looks like some like this open arcs. So you will see that these open arcs can be identified with open intervals on your real line, right? So this you can do it for any point on this figure, and so you can say that this topological space, so this is of dimension whatever call it m prime. So this is one dimensional. So immediately you can see that okay, you have this filled figure here and this figure m prime, so they are not going to be equivalent. I mean they are not going to be same, because the dimension of this figure is 2 and the dimension of this figure is 1. So this is the first invariant one can attach to good topological spaces, because they have identifications at least locally with open subsets in some fixed Euclidean space. So one should remember that this n should be fixed if you want to discuss the identification with open subsets. It should not be that at one point you find some neighborhood which sits inside R and at some other point you identify in some subset in R2, open subset. So this n is fixed, and that helps to define the notion of dimension of your good topological space. So these are the manifolds which we look at in differential geometry. So now the simplest examples are the Euclidean spaces. So you look at this n-dimensional real space. So this is actually, I mean, because locally anyway it is identified with open subsets in Rn. So actually the identification is just the identity map. So this is a manifold of dimension n. Now if you look at a circle, so you will see that if you take any point on your circle, call it P, so circle actually you can think of as a subset of your R2, right? And so it gets the subspace topology coming from R2. So the open sets in S1 basically are open balls in R2 which intersected with your circle S1. So that defines a topology on S1. So the open sets in S1, they basically look like they are generated by open arcs of this fashion containing your point P. So this is how the open sets in S1 look like, and unions of such open sets. So now you will see that such open arcs you can identify with open interval in your real line. So that's why we say that dimension of S1 is 1. It is one dimensional manifold, and yeah, when I say identification, so I would require that these maps should be continuous for whatever topologies you have, and furthermore it should also be diffeomorphic. I mean there should be differentiable functions, this identification, the maps between these two functions. So actually one can make all this rigorous, but intuitively it just means that pictorially you can see that such a thing. I mean you can always smoothen them. That means you are it's different, the smoothing of this guy, I mean from an arc to an open interval. So this can be done in a smooth manner. So actually you can you get actually differentiable identification here. So this is just saying that it is a smooth manifold of dimension 1. Now the next, another example would be to look at a sphere. So a sphere, we know that this is a 3-dimensional object, and sorry, it's not the filled one, so it is the empty object. So this is actually 2-dimensional object, S2. And so here you will notice that if you take any point on your sphere, so you can look at, so this sphere, actually it is sitting inside R3. So again, S2 acquires a subspace topology coming from your ambient Euclidean space. So here we know that the open sets are generated by open balls centered at any point. So you restrict that on S2, so that just gives you open disks on this empty sphere. So this generates a topology on this sphere, and you can now notice that this open disks, so they can be identified with open disks in your 2-dimensional plane, right? So this is what you get, and so this gives the notion of dimension of sphere, because you are identifying these open sets with open subsets in R2. So this is 2-dimensional object. And one can again see that this is actually a smooth object, because at least any open disk you can deform it smoothly to get an open disk inside R2. So we say that S2 is actually a smooth manifold of dimension 2. And another standard example is the torus. So torus is also called as the donut. So it basically looks as follows. I hope it's okay. So this is precisely, you can just take an empty tube and join the ends. So this is the donut. So here again you will notice that you can take any point on this torus. I mean, topologically you can also think of it as S1 cross S1, product of 2 circles. So you will again see that you can look at open sets containing any point on your torus, and it can be identified with the standard disk in R2. So this is actually 2-dimension. So this is of real 2-dimension. So you have, so these are certain examples, and so this tells us that for manifolds at least dimension is an invariant, and from here one can see that Rn, when for example R2 is not topologically same as R1, I mean, because the dimensions firstly are different. And now you can ask some other questions here. I mean, so here you can ask if is S1 same as S2 and so on. So okay, dimension says that, but here for example if you take the sphere S2 and this torus, are they going to be same or not? Right? Because anyway they are both 2 dimensions, 2-dimensional objects, 2-dimensional manifolds, but I mean in the picture we know that a sphere is not going to be same as the torus, right? Because the sphere, it is an empty sphere and this is the torus. So you will see that at least your torus has one hole here, and this one, the sphere has no holes. So you have to associate certain invariant which measures this property as well, which somehow encodes the number of holes. Okay, so this is the notion of fundamental group which one would look at later. So you see that you need finer invariants than just the dimension which will help you distinguish your spaces, at least the good topological spaces. And another aspect here is that, okay, once you define good topological spaces, you also want to carry out calculus on them, because in at least in physics and in many other applications in engineering, where your manifolds, I mean, because okay, we live in the three-dimensional space, but actually if you look at additional parameters, I mean, one can ask, why do you need to look at Rn when anyway we are just living in three-dimensional space? But actually in other subjects, actually like for example speed and acceleration, they also become parameters on which you associate to a system, and so hence we essentially need to look at larger dimensional spaces. And once you go into a larger dimensional spaces, you need to carry out the calculus which you carry out in your usual three-dimensional space, or rather two-dimensional space, to higher dimensional spaces. And then actually the system would also doesn't really look like a linear space like Rn, but it has some other shapes, and that's why manifold theory is relevant in other subjects, for example in mathematical physics and so on, where you have more parameters to study a system, and that requires one to look at higher dimensional manifolds. And it also becomes useful, or rather it is required to carry out calculus in such spaces. So basic question is that, okay, on your real space you are able to do calculus, but then if you restrict to some spaces which have different shapes, so how do you carry out calculus? So at least if we require that locally they all look like open sets in some fixed real space, then we know that you can carry out local calculus, because it is just looks like an open subset in some fixed Rn. So you can do local calculus, I mean point wise, neighborhood wise, you can do define continuity, differentiability, integration, everything. But then if you do something locally, you also need that this local data should be patched together in an appropriate manner so that they give something globally, right? So this is called the global calculus. So the basic question is that you need to patch local data into global objects, and this is one aspect. And the other aspect is that you want to differentiate vector valued functions on manifolds. So you have functions defined on manifolds, but your manifold has different shapes, so you can locally define your functions in some space, but in some other real space, but now you can differentiate coordinate wise. But again the point here is that if I on one open set you have functions, and if I take another open set which overlaps with the previous one, and you can still differentiate them, but then there should be compatibility on the overlaps of open sets. So the basic question is that how do you patch functions, in the sense that how do you define compatibility of objects or functions or differentiation. I mean, for example, your differential operator D and so on. How do you patch these things on overlaps? So this involves, so you have to find some other space, some other manifold where these vector valued functions take values in. So those are called as vector bundles, and so for that one actually requires to introduce certain accessories. So they are called as, so that means in the sense that you want, at least we have a notion that you have a manifold. So by definition it means that locally it looks like some open subset in something. So you just flatten this open subset, at least locally around in a very small neighborhood of P. So you can think that it is actually a real n-plane, in this case R2. So actually at any point you attach R2. So this is somehow saying that you flatten your open subset around any point. So this is called the approximation in a naive way, approximation of your open subset, of a small open subset to a given point. And then you can think that, okay, you are actually doing calculus on this R2, on this small, on this plane attached to any point. So this motivates a definition of tangent bundle. So to define tangent bundle, or rather, so which generalizes to the notion of vector bundles. So at least tangent bundles, so let us start with the notion of tangent space. So as we saw that for manifolds, that means which are good topological spaces and which comes equipped with a covering whose open sets look like open subsets in a fixed Euclidean space. So at least for any point you can associate a tangent space, so which is just a flattening of a small neighborhood at that point. So this is the real vector space you attach, and this real vector space is again of dimension n, because that's by definition, and the elements are called as the tangent vectors to x at that point P. So this you can do at any given point on your manifold. So for example, I took this point P, so I get a plane R2, and so now I can vary this point P prime. So I get different planes. I mean, this is not the finite square, but actually the plane. So I can vary the point here, and I get a collection of vector spaces, and all of them are isomorphic to R2, at least in this example. So I just take so each such plane, so let us call by T S1 at, so sorry, this is S2 at P. So this is the tangent plane at this point. Then I have the tangent plane at any other point. So you just take the disjoint union of all these vector spaces, right? So you just take the disjoint union of all these vector spaces, and so this actually admits a map to the original manifold itself. Yeah, so you take, so one can write this formally, that suppose if X is a smooth manifold, so given any point P in X, you associate a tangent space. So suppose this is smooth manifold of dimension n. So this is actually a real vector space. Of dimension n. So now you take the disjoint union of all these tangent spaces. So actually this admits a map to X itself. So because this is precisely going to be the union of, or rather the collection of all pairs P and the vector V, so that P is a point on X, and Vp is actually a tangent vector at this particular point on X. So for any such pair, you send it to so a point P and Vp. So this is sent to the point P. Okay, so this is the at least set theoretically you are able to define a morphism, or rather a map between two sets. But we know that X has more structures. It is not just a set, but it has a topological structure. It also has a manifold structure. So we would like to put some topology on this set and a manifold structure on this guy. So actually it is a theorem that indeed one can put such a structure on TP, because locally, because a manifold, at least we said that locally it is just looking like some open subset in Rn. So if I just take some open subset at some point P here, so this I know that this is looking like some open subset in Rn. So it would suffice to know how these tangent spaces to Rn look like for any point on Rn. So if I take the n-dimensional plane, if I take any point on Rn, so the tangent space is going to be itself, right? So locally, since this is isomorphic or diffeomorphic to such open subsets, so the tangent space to UP is just going to be UP cross Rn. So this is how this collection looks like over such open subsets. So you can imagine that wherever these UPs, how they patch up together, so the same patching condition will give a manifold structure on TPX also. So this is this collection, this is called as the tangent bundle, and it is denoted by Tx. So you see that this, at least locally you have obtained, because Rn is a manifold, UP is actually an open subset, so it is again a manifold. So the product has some manifold structure, and wherever the patching conditions also give rise to patching conditions on this disjoint union, which locally looks like this, and so that gives a manifold structure on this collection here, on this collection of all vector spaces. So this is again a manifold, a smooth manifold. And now you notice that the dimension of the smooth manifold is going to be 2 times n, because UP is actually sitting as an open set in Rn, so this is n dimensional object, and you have taken the product with n dimensional real space, so this is dimension 2n. So actually, as soon as you have this good topological space, which we call as manifold, you have attached another manifold, which is called a tangent bundle, which, so this tangent bundle naturally comes with the structure of manifold on your topological space. So this is something very canonical construction also. So you get a natural bundle of vector spaces. So actually this tangent bundle is very useful if you want to understand the geometry on your manifold X. So once you have a tangent bundle, so which is as we said, namely that it is a collection of vector spaces, or rather the tangent spaces. So whatever operations you can do on vector spaces, you can also carry it forward to bundles, to the tangent bundles. So for example, if you take some vector space, so the first thing you can do is that, suppose you have 2 vector spaces, so the first thing you can do is to take their direct sum. So the direct sum is again a vector space. So then you can take exterior powers, the tensor powers. So suppose V and W are vector spaces. So you can take the direct sum, and then you can take tensor powers for examples, V tensor W and so on, and you can take several copies of them, say R times and S times. So you can do several operations with vector spaces, and all those operations can be carried out to this tangent bundle as well. So for example, you have gotten hold of your Tx, so then you can take its direct sum with itself several times, so that gives you several copies of tangent bundle, and that still has a manifold structure. So you see that as soon as you have a manifold, which is a good topological space, you attach this tangent bundle, and you can have several operations, and you get actually a large collection of manifolds which are attached to your X here. And another important notion is the dual of a vector space. So this is what we know. So if I have a vector space, so then one can define its dual. So this is just a linear functions on V, the R linear functions. So again this is of the same dimension. So suppose V has dimension K, so then the dual also has dimension K. So when we have this tangent bundle, so whose fibers, the fiber of this map, the natural projection, so this is locally just a projection map where a point P and a vector is just sent to P here, right? So what we are doing here is that this tangent space you have, so you can take its dual space. So the dual vector space is called as a cotangent space, and it has the same dimension as that of the dimension of your tangent space, and you can take the collection of all the dual spaces, so that gives rise to the notion of a cotangent bundle on your manifold. So you can form several exterior powers, symmetric powers, and so on, and you actually get a good collection of vector bundles or bundle of vector spaces on your manifold. So this is what is formally looked at here. So this tangent bundle is a very special bundle because it is just at any point, it just the points correspond to the tangent vectors of your space, of your underlying space here. So actually mathematics, what you do, once you have some phenomena, you try to see what properties that phenomena has, and then you put it in an abstract way and call it as a, and form a definition, right? So what we have seen for tangent bundles is that this comes with from the structure of your manifold, and moreover we have seen that locally it is just a trivial product. It is just product of your open set with a fixed vector space, and then of course that in the overlapping of these open sets there should be good patching condition. So this is what is used to get this manifold here. So this one can put it in a more formal way, and instead of your tangent spaces you can just start with any vector space, right? I mean you have several vector spaces. For example, I can just take any vector space Rk, and I take its product and consider the first projection where so since X is a manifold, Rk is the building block, so this is again a manifold. So you have X and B, so this is sent to X here, the first projection. So this is actually a vector bundle because at any point X, the fiber is just Rk, so it's a collection of vector spaces. But this is a trivial vector bundle because at any point I am attaching the same vector space which is Rk here. So this is called as a trivial bundle. So more generally, if we want a vector bundle, so what we say is that at least locally it should look like a trivial vector bundle. So this is what is written here, that formally you have a vector bundle, so which says that it should again be a manifold, and we require that the fibers, and it should admit a map to the original manifold you begin with, so that the fibers should be all vector spaces, and the identification should be a vector space identification, so that locally at least everything looks like this trivial product. That means it is just a projection on the first vector. So this is more generally what you call as a vector bundle, and to a vector bundle, so it's a manifold, right? And you can so firstly it has a dimension, so which is same as which will be the dimension of X, because you are just looking locally, it just looks like a product of an open subset from your base, so and plus the dimension of your fiber, dimension of the vector space you attach. So you can define the dimension of this vector bundle, and then the second property you can look at is define the rank of this vector bundle. So the rank of the vector bundle is just the rank of the vector space. So for example, in this case you have the union of tangent spaces, so the rank of this tangent bundle is just the dimension of this vector space. So in this case it happens to be n. But in general, if you look at such a trivial product, I mean you have just the X and your k dimensional real space, so the rank of this bundle is going to be k. So call this E. So rank of this bundle is k, and in this particular example it is n. And locally also you can because it looks like this and k is fixed, so you can define the notion of rank. So you see that as soon as you start with this good topological space X, you are able to define another manifold, and then you are able to attach another invariant which is the rank of your vector bundle. So these are certain numbers, I mean dimension and rank and so on, which you associate to all these objects. So anyway, I would towards the end of this talk I would try to say why these vector bundles are useful to understand. See, I mean a priori it just looks like, okay, you get something which another space which covers your original manifold. So it doesn't say that, okay, how you are able to does it give information of your original X itself in some sense? So that is not clear from this description. So later we would try to attach certain invariants to vector bundles which actually correspond to certain objects on X. So that will say that most of the information which you require on X, so those can be realized as invariants of vector bundles. So that is the crux of this talk, which we would look at towards the end. Yeah. So again we come back to the question of attaching invariants to topological spaces. So basically we want to distinguish spaces by attaching invariants. So the invariants, the first the basic invariant is the dimension which is only attached to good topological spaces, but for arbitrary topological spaces you can still ask if you can, because where there is no notion of dimension, you are unable to define that notion, can you still do that? So the first thing which was introduced by Poincaré is that you can define a certain group which measures holes in the space. So holes, that if I take the n-dimensional space, so this has no holes, because if you look at this, your intuition says that there are no holes. So one says that the group you attach is the trivial group. The group is denoted by pi 1. And now if you look at the circle, so the circle, it has one hole, and precisely the winding loop, it generates your fundamental group pi 1. So in the sense that so you have the circle S1. So I choose some point here P. So we see that there is precisely a big hole here. It bounds this area here, and so you can attach, the group you attach is precisely Z, because if I choose this any point here, so you look at this loop which winds around this circle once, so that you call as the generator, so call it gamma. And now I take this loop which starts at P and ends at P once, and then I go around it many more times. So that will give me whatever, if it winds around it say k times, so that will give me a loop which I would call as k gamma. And now if I go in the opposite directions, so in this way actually if I go in this direction, I would get all the positive integers here generated by this loop which I call gamma. And then if I go in the opposite direction, I would call it to be, I put a sign to it, so I would get the negative integers here. So the group we attach to this circle is precisely a set of integers, which is just the winding number of a loop. So this is the group you would associate to your circle. And now if you look at a sphere, so this picture, so again you see that this is the empty sphere, it is not the filled sphere. So but again it has no holes, so that means we say that the fundamental group is trivial. So formally actually we want to say what does it mean to say something is a hole or not, it's not a hole. In the sense that we say that you start with any topological space, you fix a base point, and now you look at the group generated by all loops based at the point P. So if you have a topological space, something like this, of whatever shape, then I fix some point here. In most of the figures which I have drawn, so they are all connected and path, whatever notions you have about topological spaces. So at least I assume that your your spaces are connected, path connected, and so on. So that's why the the invariants you attach are independent of the point you choose, the base point you choose. So suppose if I fix a point P here, so I would just firstly take the collection of all loops. So the loops essentially are going to be closed paths, closed arcs, which start at P and end at P. So these are called the loops here. So you can look at the collection of all such things and they can be of whatever size you have, shapes and sizes here, it doesn't matter. So you take the collection of all such figures here. So this is, you can see that, I mean, if your space looks like something like this, so this is going to be a very big set, and now you can put a group operation on it. So namely that if I take two loops, I can add the two loops just by following the first loop. This is the first loop, and then if I want to add it with the second loop, then I just concatenate with the second loop here. So that is still going to be a loop based at this point. So this is the addition of loops. So if I do this, and if I want to define the difference, so I just go in the opposite direction. So the loops come with a direction also. So once you do this, so you are able to put a group structure on the set of all loops based at a fixed point here. So now see that if we want to attach an invariant, it should be something tractable. Tractable in the sense that it should be something computable, right? I mean, we don't want just to define some objects just for the sake of it, but at least we should be something computable. And you see that if you just take this collection of all loops and you are able to put a group structure, there is no way one is able to compute this group. It's going to be uncountably generated and so on. If your X has uncountably many points, this space of loops also is going to be infinitely generated, uncountably generated. So this is not good to look at. So you put an equivalence relation. So what we have just said is that you take the collection set of all loops based at some point. So this is a group. So the group is just following the paths in whatever direction you want. But this is a bad group, so you put an equivalence relation, and the purpose of putting an equivalence relation is basically to cut down the size of this group. I mean, in any case, in any situation, I mean, if you have looked into ring theory, module theory, or in other subjects, you put an equivalence means basically you cut down the size of your bigger object, and the quotient, I mean, then those are going to be your equivalence classes, and that is in many cases happens to be tractable and useful actually. So one has to see what equivalence you can put on this collection of all loops. So this is just saying that if you take two loops, you say that they are same. Equivalent means they are just same if one can be continuously deformed into the other loop. So this is just saying that I begin with one loop, I fix a base point P here, and I take some loop here like this, and then I say that this loop is same as this loop. So this is another loop. So why this is, you want to identify them, so you can, not why, I mean how you can identify them. Actually you can just deform the bigger loop which goes around the smaller loop here, just by, you just shrink the bigger loop, that means you actually deform it and identify it with the smaller loop. So this is, so that means actually what, so this is just a picture, but actually what it means is that you are just continuously deforming, because you have not lifted this bigger loop outside this blackboard, so it still remains in this topological space, you have not removed it, so this is just moving along this path and so on. So you go send it, push it closer while remaining inside this topological space, while remaining on X, right? So this is the identification. So this says that this loop gamma, it can be deformed into this smaller loop gamma prime without taking the loop outside X. So this is just what it means. So this is the equivalence relation. So now you see that if you do put this equivalence, then actually it cuts down, it identifies lot of loops. In the sense that now suppose if I just take this topological space which looks like this, you will see that all the loops can be shrunk to a point, and this loop you can also decrease the size of it as much as you want, then actually just you end at the constant loop based at P. So immediately, I mean, if you think, reflect on it for a little while, so you see that the pi 1, the group attached to it, that means the set of all loops modulo this equivalence relation, at least in this example, as a subset of R2, the field 1. So this is just going to be the constant loop based at P. So that means it is trivial in this case. So now we will see that, for example, so this is, I mean, when you want to attach some, you want to look at example where this is non-trivial. So let us look at this example S1, the circle. So because we already said that you are able to attach the ring of the group of integers in this case. So now you see that if I take this P, if I just look at this collection of loops without this equivalence, so actually if I just of this bigger loop slowly, I mean continuously, I mean I am not taking this bigger loop and taking it out of the board, it still remains on S1 itself. So I do this, then I come slowly back, and then I can shrink the size of that loop and till it comes to the constant loop based at P. So all such loops which do not go around this circle, so they are all shrinkable to a constant loop. Only those loops which complete your winding this circle, so they correspond to an element here, right? So because those things cannot be shrunk to a constant loop here. So that's why we get the ring as a group of integers attached to this equivalence relation, to this object here. So this gives a non-trivial example, I mean an example with a non-trivial fundamental group. And again, if we look at this example of a sphere, so this is again not the filled sphere. So in this case, the loops are going to be something which lies on the surface of the sphere. So you see that any such sphere, any such loop can also be shrunk slowly, I mean continuously, till it comes to the constant loop based at that point P. So again, in this case of a sphere, you notice that the invariant you attach is trivial. So this again says, I mean this circle, it has a hole, I mean it has a big hole, but this sphere, it has no holes, and so pi 1 does not capture anything, I mean it is trivial here. And this guy also has no holes. For example, if this guy, I mean this topological space looked like something like this, where it is filled up here, so that this object, the points inside this thing and in this area, so this is not included in your topological space. So now you see that if I take a loop which goes around this, so this is not shrinkable to a constant loop here, because this cannot be, I mean because I have to do it continuously, so I cannot break the loop and so on. So that's why such loops exist, and then one can check that the pi 1 of this space where this area is removed, so this is still going to be Z, because the loops which go around this empty space, they qualify to be elements in this quotient here. Okay, so this is what the fundamental group does, or rather captures. And another fact here is that when we study groups and so on, I mean you want to attach invariants, we want them to be good groups. I mean, so what are the good groups you can say? I mean the first thing would be if something is abelian, I think many of us are happy that because commutativity holds and you can do many things. So at least we require that your group you attach is certain, is abelian. And another thing is that in many cases still these groups, I mean these are some nice examples which I am able to show, but you can imagine that if I just take any arbitrary topological spaces which have many bad holes and so on, then the fundamental group, it can be very huge with many generators and so on, and it can be highly non-abelian also. So somehow we want to take care of this aspect. So at least the abelian part we can take care of it, because for example if your fundamental group, if it is not abelian, so what do? So it's just some algebraic operation that you take the commutator group and then you go by its quotient. So once you do that, what you get is an abelian object. right? Because commutator precisely has those elements which do not commute, right? So which do not commute with other things. So you go modulo those things. That means you kill them, and so what remains is the abelian part. So corresponding to this any group, you can do this. So this fundamental group, you go modulo this anti-commutating elements, and what you get in the quotient is an abelian group. And for this topological space, let us denote it by H1. I mean, there is a reason why you have pi 1 and H1 here. So at least pi 1, one can ask why 1 is there. So one can imagine that there might be some pi 2, there might be pi 3 and so on. So those are called homotopic groups, but which we won't look at today. But at least we see that you look at this quotient and you have this abelian group H1. So at least, so the basic question for us is to have topological spaces where which should be computable, and so in that sense, at least the first aspect we have gotten something which is abelian. So we would restrict to those classes where at least H1, where at least if you go modulo throughout this anti-commutating part, so at least this is something tractable in the sense that it is a finitely generated abelian group. And this does happen for good topological spaces. So good, I mean this, I mean at least for compact manifolds, these groups H1, which is the quotient of your fundamental group. So this happen to be finitely generated abelian groups. So at least we have got, at least theoretically we have an object which by certain theorems which we know that this is finitely generated. And now, okay, so if I look at loops, the collection of loops, so loops are actually one dimension, right, because it is just the image of R1 where you identify 2 points, or rather an open interval or rather closed interval in R1, and you identify the endpoint. So these are one dimensional object on your topological space. So if you want to study topological spaces, you are not going to restrict yourself to one dimensional objects, because that associates, that corresponds to these groups pi 1. So you can imagine that if you take some higher dimensional subspaces, closed subspaces, you should be able to attach certain groups corresponding to that data. So this says that, okay, I mean instead of one dimensional loops, I should look at some closed spaces, I mean something like surfaces inside your bigger topological spaces and so on, and they have to be closed, and so that, and if you look at some equivalence on the collection of all such surfaces, that should correspond to a certain group, and that should also be something computable, that means tractable. So this leads to cohomology theories. So at least for compact, I think I have a time, maybe I'll take 5 minutes and stop. So this is precisely, so the motivation to look at singular cohomology and all is basically because it sort of generalizes your study of your fundamental group by going from one dimensional loops to higher dimensional closed subspaces, and basically you are just, at least for good topological spaces like something like compact complex manifold, you are just taking the collection of closed subspaces of a particular dimension, and then what you do is that you put another equivalence, because if I just take the collection of all closed spaces and I just take a formal linear combination of such closed subspaces, so then I get a group structure on such collections, but this is still going to be very bad. So I put a homological equivalence where one can still say that if one collection is of subspaces can be deformed to another collection where the deformation is within the topological space where you don't come out of it, so then you say they are homologically equivalent. So you do that, so what you get are the singular homology groups. So you have Hi there, so that I says this is for dimension I, so Zj are closed subspaces of dimension I here. So at least for good topological spaces, compact complex manifold, this definition will correspond to your ith homology groups. But many cases, if you want some kind of properties, it's convenient to look at the dual theory, that means the dual objects. So at least you can have with Q, I mean the rational numbers, Q is the field of rational numbers, so you can define a dual theory by taking duals here. So the basic fact here is that at least for good topological spaces like this, these groups, like for example H lower 1, H upper 1 and so on, which goes till the dimension of your manifold. So these are all going to be finitely generated abelian groups. So you see that if you have a good topological space, you have attached finitely generated abelian groups, and these sort of so these are all topological invariants, that means the groups attached to it. And you can see that now if you want to distinguish your spaces, you just need to look at these groups and see if they are the same or not. At least if you know that they are not the same, it will immediately tell you that your spaces are going to be different. But this is not, converse is not true. You can have spaces with same homology groups. And in the last 2 minutes, let me just say that how do you capture. So at least for some nice class of topological spaces, we have defined attached certain groups, and but we want to capture these classes as well, because if I just take any topological space and subspaces, closed subspaces there, I want to realize it as a geometrical object. That means it should be attached to certain vector bundles like tangent bundle and so on. So this is the last page. So it just says that you just as when you look at a topological space X and you looked at subspaces and formed a group and so on, so similarly you just take the collection of all vector bundles and put some you make it into a group by putting signs to it and coefficients which lie in integers, and you put some equivalence relation to any vector bundle. You attach invariants which are called the Chern classes, or rather the Chern invariants, which lie in this even degree cohomology. And it's a theorem that you have a map which is actually a ring homomorphism, because when you look at the collection of all disjoint union of all these cohomology groups, it also has a ring structure. And so it basically says that this Chern character, which associates invariants to vector bundles and which corresponds to classes on your X, so that's an isomorphism. So in other words, it just says that the classes in your homology groups which come from closed subspaces on your topological space, many of them, I mean most of them, at least in even degrees, so they can be captured by invariants to vector bundles, which are certain covering spaces of your manifold. So I think I'm over time, so sorry for that. So thanks. Are there any questions or comments? Yeah, maybe some standard references for topology. I think there's a book by Munkus. I don't know the title of this book, and I think there are books by Massey and so on. I think the singular cohomology, I think you can find it in Massey's book. And I think this is called general topology maybe. Yeah. And I think there are other books by Fulton also. I think maybe it's called algebraic topology. Yeah, I think there are many good books now available in the market, but I don't know the details of the title and so on. I hope you can find it. Yeah, so I think the organizer Parmeshwaran, he told me that all of you have to fill this feedback form, and maybe tomorrow afternoon somebody will come to collect it, and so you can write your comments on this program, and mostly they would go through this feedback form and try to make any improvements for the next program whenever it happens. So those who did not receive the feedback form, so probably tomorrow again in the morning he would give it out, and you can make your comments then.